Hi, this is Forrest Briggs. In this series of videos, I'm going to be explaining pterodactyl. Pterodactyl is a suite of command line tools and C++ classes for machine learning and signal processing, primarily intended to be used for automatically recognizing bird species from audio recordings collected in the field. So as we begin this series of videos, the first thing I want to call your attention to is where you can get the source code and precompiled binaries. So the URL is github.com/fbriggs/pterodactyl. And here you will find an Xcode project. This will work in pretty much any version of Xcode. The source code, you can take a look in there, and precompiled binaries. Right now, only I'm offering one for Mac. So in the rest of this tutorial, we're going to use this precompiled Mac binary. Now, before we get into the specifics of how to use pterodactyl, I want to show some examples of what we're going to try to do with it. So what we have here is a folder full of audio data that we recorded in 2009 in the Cascade Mountains of Oregon. And as you can see here, there are 7,688 20-minute audio recordings in WAV format. And these were all just collected, using Songmeter SM2 audio recording devices. And so, at the end of the process that we apply through pterodactyl, what we will have done is split those all up into more manageable 10-second chunks of audio, and then computed a spectrogram for each of those chunks, and done some analysis to find where the bird sounds are in those spectrograms. And the final output will look something like this. These are all black because that's no sound. But anyway, okay, right. So what you see here is a spectrogram for a 10-second chunk of audio from this data set, and the red outlines are showing regions of the spectrogram corresponding to bird calls, and this can potentially isolate multiple sounds even when they're overlapping in time, as long as they're not also overlapping in frequency. And in addition to just finding out where all these calls are, there's a lot of other data that gets generated in the process, like feature vectors describing each segment and other visualizations and so on. So this is what we're going to generate, and the remaining videos in this sequence will show how we start from this original data and get to this final output. Alright, so now we're going to get started analyzing some data using pterodactyl. For this demo, we're going to assume that we have these three audio files here. These are each 20-minute WAV files. Let's see if we can find some bird sound in there. Alright, and I'm going to do this in this pterodactyl demo folder that I created, and I've downloaded the Mac binary from the repository and renamed it to just pterodactyl without the version number at the end. And so the next thing I want to do is use terminal. So I'll open a new terminal and then change directories to the pterodactyl demo folder. And I'll run pterodactyl with no arguments to get a list of help or example usage. So this isn't a necessarily completely accurate list, to be honest, right now. The best way actually to know exactly what it's going to do is to look at the code in main.cpp, where it actually parses the options that you pass to it and then executes whatever function. But, that's why we put this stuff in open source and clean it up over time. So anyway, the first thing we're going to want to do is run pterodactyl with the setup option, and then that's going to create a bunch of folders for us. Oops, I need to do /. Alright, there we go. Okay, so now you see it's created all these folders, and as we run through the machine learning and signal processing pipeline, it's going to use a bunch of these folders to either read from or write to whatever data it's processing. So the first thing we're going to do is copy all of these 3 wave files that we want to process into the source waves folder that we just created when we ran the setup argument. Okay, now we won't really need this anymore. So the next step is actually to split up these audio files. We don't really want to work with 20-minute audio files. It's much more convenient to work with 10-second chunks of audio files. So we'll look at the options for how to do that again. Okay, now we see here one of the options that we can pass is split, and then the first argument will be the number of seconds in the chunks that we want to create. The second argument will be the name of the folder where it should read the original files, and the third argument will be the path to the folder where it should write the split up chunks of wave. So when we ran setup, it already created all these folders. Here's source waves, here's chunks. This is where we're going to write the chunk files to at the end. So we can just copy this, execute it just like that. Now the original files were stereo, so it's going to convert them to mono. This whole system doesn't really do stereo at all. Okay, so you see now that in the chunks folder we have a bunch of much smaller wave files. These are all 10 seconds long. And that's what we're going to use as we continue to work through the pipeline. In order to get the most out of pterodactyl, I recommend that you run it on a machine that has a fairly large number of CPUs. For example, I'm running it on a machine with 2 quad-core Intel Xenon processors, each of which is dual hyper-threaded, so essentially I can get 16 parallel executing threads. And for the most part, that leads to almost a 16x speedup when I'm running pterodactyl on large amounts of data. So, for example, we just saw how to split up these 3 source wave files into a bunch of 10-second chunks, and we can do that in parallel as well if we use the split multi-thread command with the same arguments. Now, that's one thing that's actually not documented in the help message, but you could find it if you're looking here in main.cpp. Okay, so now we're going to split with the multi-threaded version of the command. And we can watch the activity monitor here. It's going to spike up a bit. Oh, I guess it's already done. But anyway, actually in this case it was probably only using 3 threads because there were only 3 files. But if there had been 16 or more, we would have used 16 threads. And we'll see some other parallel computation as we go further along. So, I guess the lesson to be learned here is read this section of main.cpp, and if you see a version of something that has an underscore multi-thread, that can potentially be a faster way of doing what you're trying to do. Okay, so we started out with these 3 20-minute audio files, and we converted them into 360 10-second chunks. The next step will be to compute spectrograms for each of these 10-second chunks and apply a noise filter. Now, if you check the documentation here, you'll see that the commands are listed in basically the order that we might want to apply them in a typical use case. So we already ran setup, then we ran split, and then the next 2 steps will be spectrogram and noise filter. And we could run these 2 commands sequentially, but there's a faster way to do this, which is to run both of them in one step, and the command for that looks like this. You could find that documented here in main, and if you're willing to read the C++ code, you look up this function, make spectrograms and apply noise filter multi-threaded. You see that it takes 3 arguments. The first is the source waves folder, the second is the destination spectrograms folder, and the third is the destination filtered spectrograms folder. So if we come back to my command here, see that I'm passing it 3 folders. Chunks, that's the source folder that I want to apply this command to. Notice that I'm not applying it to source waves. I don't want to compute the spectrograms for these 20-minute audio files. Instead, what I want to do is compute them for the 10-second chunks. And then the output or result of running this command will be written to these 2 folders, spectrograms and filtered spectrograms. Okay, so now here we go. I'm going to run it. You'll also see that our CPU usage spikes up to 1600% for just a moment here. And now I've got my output. So in the spectrograms folder, I now have one bitmap image file for each of those original 10-second audio files. And these are the spectrograms. A spectrogram is an image that represents the intensity of the sound as a function of time and frequency. Time is on the x-axis and frequency is on the y-axis. So these shapes and patterns that we see here correspond to different species of bird call. And then if we come up here to the filtered spectrograms folder, this is the result of applying a noise filter to each of those spectrograms. And this can help in a lot of cases, not always. It's pretty good for removing stationary noise, which would be sounds like wind as long as it's not too gusty. The next few steps of the process will involve training a classifier to automatically segment spectrograms into regions corresponding to bird sound versus background noise. But in order to do this automatically for a whole bunch of spectrograms at once, we need to provide a few manually labeled examples of correct segmentation. The first step will be to copy a random subset of the files that we just created, the spectrogram files, into a folder that will be used by the machine learning system as examples of correct segmentation. So there's a command that pterodactyl provides to help us do this called copy random subset, and it takes 3 arguments: a source folder, a destination folder, and a number of files to copy. So we're going to want to point it at the filtered spectrograms folder. That will be our source folder. So we're going to copy some of these 360 spectrograms chosen at random. The destination folder will be segmentation examples. This is the folder where the system looks for examples of correct segmentation. And then finally we'll specify that we want 10 files to be copied. Okay. Just make the window there a little bit bigger so you can see the command. Now I'm going to execute this command, and the final result... Sorry, I'm having some trouble with the mouse here. Okay, the final result is that we have 10 files chosen at random that end up in this segmentation examples folder. And these are the files we're going to label as examples to the segmentation system. Okay, so these are the 10 files that I just copied randomly from the chunks folder to the segmentation examples folder. And then there's one more file here which I'll talk about in a moment. But what I'm going to do is take one of these files and open it in Adobe Photoshop. Now the first thing I need to do is change the mode of this image. Currently it's in grayscale or indexed mode, and we need to change that to RGB color because we want to draw on it in red. So I'm changing the mode to RGB. Now I'm going to go to the color selector and make sure that my color is 25500. That's pure red. It can't be anything other than that. It has to be exactly 25500. Now I want to choose the pencil tool, not the brush tool, but the pencil tool, and an appropriate diameter. 13 is okay here. It really depends on what your spectrogram parameters are, but for the ones that are set by default, 5, 9, or 13 would be all fine choices. Now it's pretty important here that I use a hard pencil tool, so this is just a like non-anti-aliased, non-smoothed brush. I don't want to use a brush like this that makes a soft stroke. I really do want the pencil tool here, which will make a harder stroke like that. You can see if we zoom in, there's crisp pixel level boundaries. Okay, so what I'm going to do is take my red brush and draw over the regions of the spectrogram that correspond to bird sound. So each of these little white areas here is actually one bird call. That might be a Pacific slope flycatcher. I don't have to be super accurate as I draw this, but if you want to spend more time and get it really accurate, it might make a difference. There's a little bit of a horizontal smear on some of these calls, which is partially a result of echoing in the forest canopy. Which means it's maybe a little harder than you might think to say exactly which pixels of this are or are not bird sound, but it doesn't really matter that you be super accurate about it. So here we go. Now I've drawn over all the bird sound in red, and I'm going to save this file as a Windows format 24-bit BMP. And if I come back to my folder here, you see that before I modified it, it was a 321 kilobyte file. That's because it was only one channel. Now, after I've modified it, it is a 1 megabyte file because it's 3 channels. Now, it doesn't really matter that we drew over the raw spectrogram data in this case, because what the machine learning system is going to do is it's going to look for the original spectrogram with the same name in whatever folder we tell it about. So there's still a clean copy of this here in the filtered spectrograms folder, for example, right? So that's okay. And if we come back to the mask that we just drew in red, the way this will actually work is that we'll build a classifier which takes as input features describing the region around an individual pixel of the spectrogram, and all the pixels that we labeled in red here will be treated as positive examples, and all of the other pixels will be treated as negative examples. Now, another thing we can do is specify examples that we really want to avoid. And this is a good idea when there are other loud noises which might confuse the segmentation system. They're not necessarily bird sound, but some other loud noise. So a good example of this is rain. So if we take a look at this spectrogram here, you can see these parallel harmonic lines are bird sound, but then all of the vertical streaks are actually raindrops falling probably not mostly on the microphone, but in some radius of a few meters around the microphone. And so, because these also kind of look like bright lines in the spectrogram, the segmentation system could often be confused by them and mislabel them as bird sound. So to avoid that, what we can do is provide some examples of spectrograms where we mark in blue anything that we specifically want to avoid. So this is the same spectrogram I just showed you before with the rain, and then the red parts are the birdsong, and the blue parts are rain that we want to avoid. And I snuck this one in between the previous clip because the 3 audio recordings I chose at random there, none of them had any rain in it. So I wanted to show an example where there was some rain. Okay, so in a normal use case, what you would do is you'd go through all the files in this segmentation examples folder, and you'd annotate them to look like this, where you're marking the positive pixels in red and any really negative pixels in blue. And then we're done with this step. And by the way, for most of our experiments, we'd probably do this for at least a couple hundred files, not just 10, but for the sake of this demo, I'm only going to use a handful. Okay, so I'm just going to do the same thing to a bunch more spectrograms. This doesn't really take that long. You can probably get through at least 100 in an hour. So as I mentioned before, blue would be the color we use to highlight things that we want to try to avoid. Just as we use 255.00 for red, we want RGB equal to 00255 for blue. And some other stuff you could use it for besides rain. You might use it for sounds from an airplane or other motor vehicles. Oops. Okay, here's it. This is interesting. So it's drawing in gray right now because I didn't change the mode. So once I change it back to red, then we'll have the proper color. Okay. Not sure. That might actually be... I can't tell if that's a thrush or a motor vehicle. Okay, this is another interesting case. Here we have a 10-second chunk where there really wasn't any sound. So we still want to go ahead and convert that to RGB, but then we'll just leave it completely blank. We could put no pixels in there. Or, let's say this was no bird sound, but it was actually an example of, say, thunder or something else loud like that. We might just scribble some blue around on it, and that will increase the weight of this training example as a negative example to the machine learning system. That's the one I already did. Okay, now we're done. We've labeled 11 examples. We probably should have labeled 200 or more, but 11 will be enough for the demo. So these are the 11 training examples that will go into the random forest pixel segmentation system. Now we have a collection of spectrograms labeled with examples of correct segmentation. These can be used to train a machine learning algorithm to automatically predict the correct segmentation for many more spectrograms. So just to reiterate, these are our labeled spectrograms. The pixels highlighted in red will be positive examples, and pixels in blue will be negative examples, as will any pixel that is left uncolored, although the weight is higher for blue than uncolored. Okay, so the command we want to run here is 2drfsegtrain, and it will take two arguments: the path to a folder containing the spectrograms, and a path to the folder containing the annotated spectrograms. So for the second one, obviously we're going to pass segmentation examples. And for the first one, we actually could pass either spectrograms or filtered spectrograms, as long as we're consistent about what we do in subsequent steps of the pipeline. Basically, this comes down to whether we want the pixel level classifier to process features derived from the noise filtered or non-noise filtered spectrogram. And there are different situations where one or the other approach might be better. But I don't want to get too into the technical details right now, so all you really need to know is you can copy this line and the first step here is it processed the 11 files that we had in the segmentation examples folder, and it computed features for a sample of the pixels from those. So in this case, it actually took a sample of 50,705 pixels, and each pixel is described by a 547-dimensional feature vector, which characterizes the pixels around it in a box as well as in a column. And then it builds a random forest. That part is automatically multi-threaded. You don't need anything special there, but it's building this random forest, which we'll later use to predict the segmentation for other spectrograms. And the random forest model that it generated is saved in this file, segmentationrfmodel.txt. So in the next step, we'll load that model and apply it to all the remaining spectrograms in the dataset. In the previous steps, we built a segmentation model based on some examples of correct segmentation. The next step will be to apply the model that we just built, stored in this file here, to all the remaining spectrograms in the dataset. If we look at the documentation, we will find this command, 2drfsegrun. It takes one parameter, which is the source folder of spectrograms that it should process. So remember in the previous step we passed filtered spectrograms as one of the arguments when we were training the system. Now we're going to pass filtered spectrograms again as we apply. That prevents feature train test distribution mismatch. So if we had passed spectrograms here instead when we ran the training step, we would also want to pass spectrograms here instead of filtered spectrograms. Anyway, all you need to do is copy this command and then execute it, and it will initiate the segmentation process. So while this is running, it's going to be running over 361 spectrograms, and it will be writing results in a variety of these different folders. So one place that it will write a fairly interesting visualization is in this segmentation outlines folder. This is just for visualization. And what you see is the original spectrogram and then outlines in red of the regions that are predicted to be birdsong by the segmentation algorithm. And this is actually one of those examples where we had rain, so all these white vertical lines are raindrops, and the segmentation algorithm was smart enough to avoid those and only highlight the birdsong, primarily because we marked these raindrops in blue when we described them in the training examples. Okay, so we can take a look at a couple other examples of its predicted segmentation in the output. Okay, some other folders where we might see some output. This segmentation mask folder shows a binary mask just corresponding to the region that is predicted to be birdsong. So black would be predicted as background noise, and white would be predicted as birdsong. And actually, internally, there's also not just a binary segmentation that's generated, but each pixel is associated with a probability to either be bird sound or background noise. And then that gets stored in these segmentation probabilities files. And inside of it, it applies a Gaussian blur and then a threshold to produce those binary images that you saw just a moment ago. But if you wanted to access the probabilities directly, they would be in this folder. Okay, now notice that this is taking kind of a while. This is probably the slowest step in the process, so we're taking about an average of 12 seconds per spectrogram to do this analysis. So I'm going to cancel this, and next we'll see how to do it in parallel. Alright, so just a minute ago we ran this 2D RF run command to generate the predicted segmentation for the other spectrograms in the dataset. We saw that that was taking a while, so now we're going to see how to do that in parallel. It's very simple. All I do is add the multi-thread suffix to the name of the command, and away we go. So if we watch the activity monitor here, very soon this will spike up to almost 16 CPUs being used, 15 and a half, and this will all go a lot faster. So instead of doing one at a time, it's doing 15. You might wonder why this takes a long time to begin with. The answer is each one of these images that it's processing, it has to look at each one of its pixels, and there are 256 by 1,246 pixels, so 318,976 pixels per spectrogram. And for each one of those pixels, it has to compute a 500-dimensional feature vector, and then apply a random forest consisting of 100 trees to that feature vector, and get the average vote on whether that pixel is bird sound or not, according to those 100 trees. So that's what's going on here as we're running all this CPU power. But the good news is it's easy to parallelize. Just look at each file, one file per thread. And we can see here that the average time per spectrogram now, instead of being 12 seconds, is closer to 1 second when we take into account the parallelization. So you can do this with fairly large data sets. I believe I did it with 92,000 segments, and it took a couple days. Alright, well, I'm not going to make you guys wait until this gets all the way to 361, so we'll just skip ahead to that in the next video. Okay, so now we've run our automatic segmentation algorithm on the whole data set, which means that for each of our 360 or 361 spectrograms, we have a binary mask that splits it into bird sound or background noise. So I'm just flipping through them very quickly here using the preview tool in macOS. So what we're going to do is say that each one of the connected components in this image is one segment or distinct utterance of bird sound. And we want to isolate each of those connected components and compute a feature vector to describe it. So to do that, we're going to run the analyze segments command. This takes two arguments. First is the path to a folder of spectrograms. It will look at the image data in those spectrograms as part of its computation of the feature vectors for each segment. The second argument is the path to the folder containing the segmentation mask. So it's this folder, like what we're just looking at. Okay, so we can just copy and paste this. There are a few other options here that I'm not going to go into, but if we just use it as is, this will work. Alright, here we go. This part's pretty quick. There's a lot less data to process at this stage because we've already determined that most of the pixels in the images are noise. Alright, so at the end of running this, we've created a whole bunch more text files that can basically be thought of as a database which describes the data set. So the first table in that database is a map from indexes to file names. So the terminology we use is bag ID, which comes from the connection to multi-instance multi-label learning. But basically think of it like this. These were some of the files that we started out with that we generated spectrograms for. Like you see here, this is the name of one of our spectrograms. And it's being associated with bag ID 4. So when we say bag ID 4, we'll be referring to this particular file name. Or the same thing with a .wave extension if we wanted to talk about its wave data. So this file, bag ID to file name, got generated when we executed the analyze segments command. Okay, the next file that got generated is segmentfeatures.txt. Let me open this in a better text editor. Okay, so there's three columns basically. The first is bag ID, the second is segment ID, and the third is feature vector. So the way we can read this is the first column is telling us this is a segment or a connected component in bag ID 0. And if we wanted to know which image that was, we could look it up in bag ID to file name and see that that's PC 13 2009 06 blah blah blah. Okay. The next column is segment ID. So the idea is if there were 10 segments in one image, then there would be 10 distinct segment IDs associated with that one bag ID. And then all the remaining columns are a feature vector, something like 30 to 40 dimensional, describing all of the characteristics of the segment. Some other interesting data here. Segment rectangles gives kind of a more simplified view of the segments. So it has the same number of rows as segment features because each of them has one row per segment. But here what we have is bag ID, segment ID, and then the X and Y pixel coordinates in the image that bound the segment. So depending on how we have things configured, we might get a folder that contains those boxes, but I don't think I have that set up right now. But this is useful if you want to build a GUI or something like that later on, or you want to do some subsequent feature extraction. This way you can know exactly where the segments are. Okay, and it looks like that's about it as far as what gets generated. We also fill in some folders like this segments folder, so each of the rectangles within the image corresponding to a segment becomes one file in here, and the file name is bag ID, segment ID. So that's a pretty useful thing to have. Alright, so we just extracted all the segments from the dataset, and now one thing that we can do pretty easily, which is fairly informative about the characteristics of the data, is to generate a visualization of those segments. So if we look at the documentation here, the next command of interest is segment mosaic. Alright, so when I ran that, it created this file here. And this is sort of like the Rosetta Stone of the segments in this dataset. So, let's see. As I mentioned before, each row of this text file corresponds to one segment, and similarly, each image in this folder corresponds to one segment. So there's 2,923 segments that were identified in all of the dataset. So roughly speaking, around 10 segments per 10-second spectrogram. And all of those segments appear in this image, and they're ordered in a way that's sort of just a greedy heuristic to minimize the image size. But it's cool, actually, that even that simple ordering heuristic tends to group different types of calls together. And that's really just a coincidence. We can do much better by other means. So, in conclusion, this mosaic option, you have to first have done the segmentation, but once you've done that, you can run it to get a visualization of all the segments in the dataset as one image. At this point, we can do another type of visualization where we cluster all the segments based on their feature vectors, and then generate an image for each cluster. The command to do this is cluster segments. It takes one argument, k, which is the number of clusters to use in k-means clustering. So I'm going to run this with k equals 25. Okay, so the output will be written to this folder clustered segments, and there's going to be one file for each cluster, so in this case 25 files, and each file is an image of all of the segments that ended up in that cluster. So there's a couple of uses for this. One is just to explore the variety of calls that appears in the dataset in a relatively efficient way. And another is sort of as a sanity check on whether everything is working correctly. If you're not seeing fairly homogeneous clusters like this, then chances are the feature vectors aren't doing a good job of capturing the similarity between segments, and there may be a problem at some point in the process. Another file that gets generated here is segmentclusters.bmp, and this is just a single file that combines all of those images into one. So we can look at it this way. In some machine learning formulations, it's useful to have feature vectors describing the individual segments. For example, single instance, single label classifiers would typically use this kind of feature. And if you need those features, as we discussed earlier, those are in segmentfeatures.txt. However, other types of formulations, for example multi-label classification, might prefer to have a feature vector which describes the audio recording as a whole, not the individual segments. And that feature vector should be of a fixed dimension, regardless of the number of segments in the recording. So with pterodactyl, we can also compute a feature vector of that variety. If we look at the documentation here, the command we want to use is histogram of segments. So I'm going to run that command. And what this does is, first it applies k-means clustering with k equals 100 to the data set. It's very similar to what we just saw in the previous visualization. It's clustering all of the segments based on their segment level features. But then to compute a feature vector for each recording, what it does is look at each of the segments in that recording individually and find the cluster center that it's closest to, and then count the number of times each cluster center was closest. Normalizing that vector of counts gives a histogram of cluster frequencies, which can be used as a recording level representation. So the output, or the result of running this command, is that we generate this file histogram of segments.txt. And what you notice is that we have a bag ID and then a 100-dimensional feature vector. The reason it's 100-dimensional is that there were 100 clusters when we formed our codebook. And this file has one row per audio recording, as opposed to one row per segment. Okay, in this last section of the video tutorial, I'm going to point out a few more features of the pterodactyl toolchain, which are maybe less well documented and might require you to dig into the source code to really figure out how to use them. So remember that if we look in main.cpp in the main function, that's where we'll find actually where it parses all of the commands. And we've been working our way through these commands. We've seen a lot of them so far, but there are a few that we haven't seen so far. So the last one we covered was histogram of segments. Another option which will create even more bag level features, or recording level features, is this more bag level features one. Ring classifier is another option we can run, which requires some additional folders to be created where data has been sorted into heavy rain versus not so heavy rain examples, and then it will build a classifier that can filter out recordings that have so much rain in them that the pixel level segmentation really won't work. And then these two functions here about multi-label classification require that several other files have been created which specify the bag level label sets, or in other words, the set of species that are present in each recording. And then if you have that all set up just right, it can do the full multi-label classification experiment where it trains several different types of classifiers on the histogram of segments features and then computes multi-label classification performance statistics to summarize the results of the experiment. Another interesting function in main here is do non-CLI stuff. This is just a collection of functions that I've called in the course of using pterodactyl, not as a command line tool, but as a collection of classes and functions. So there's a few things in here that kind of don't fit into this general purpose pipeline, but are more specific to particular use cases. And some examples of that, if you look in this folder dataset specific, you'll find two files that are all about data analysis I did on either recordings collected in the H.J. Andrews Long-Term Experimental Research Forest, or preparing a dataset for the MLSP Kaggle competition. And so these files contain just sort of uses of this API for the purpose of processing a specific dataset. So you can look at those as examples of what else you can do with this code base outside of the CLI.